Linear Algebra 2, Tutorial 4, Kernel and Image. Problem 1. Let G be a linear map from the linear space of all polynomials of degree at most 3 to R3, sending the polynomial f of x to the vector whose first coordinate is f of 0, the second one is f prime of 0, and the third one is f of 0 plus f2 primes of 0. Find a basis in the kernel of G and a basis in the image of G. Solution. The easiest way to find a basis in the kernel and in the image of a linear map would be to determine the matrix of this map in some basis. So the easiest way for standard vector spaces would be to use a standard basis. The standard basis in the vector space of all polynomials of degree at most 3 consists of the polynomials 1, x, x squared, and x cubed. The standard basis in R3 consists of the vectors e1, e2, and e3. So e1 has first coordinate 1 and the rest is 0, so e2 is 0, 1, 0, and e3 is 0, 0, 1. So in order to determine the matrix of G, we need to take the elements in the standard basis of the original vector space, apply G, and write down as columns the coordinates of the outcomes with respect to the standard basis in the target vector space. So let us compute the images of the polynomials 1x, x squared, and x cubed under G. So g of 1 is equal to the following. So f of 1 is 1, f prime of 1 is 0, so it's 0. So f of 0 is 1 and f2 prime of 0 is 0, so it's 1. So g of 1 is equal to 1, 0, 1. So g of x evaluated at 0 is 0. The derivative of x is 1, evaluated at 0 it's 1. So f of 0, as we already know, that this is 0, and f2 prime, the second derivative of x, is 0, so it gives us 0. So g of x is 0, 1, 0. G of x squared. So here we have 0 to the power 2, which is 0. So here we have 2x for x is equal to 0, which is 0. And here we have 0 to the power 2 plus 2 evaluated at 0, which is 2. So g of x squared is 0, 0, 2. And g of x cubed, so the value of x cubed at 0 is 0. The derivative is 3x squared, the value at 0 is 0. And here we have 0 plus the second derivative is 6x, which is also 0 at 0. So g of x cubed is 0, 0, 0. Consequently, the matrix of G in the standard basis is the following matrix, which we read column-wise: 1, 0, 1, 0, 1, 0, 0, 0, 2, 0, 0, 0. So these are just these four vectors assembled as columns into a matrix. Now, if we want to determine a basis in the kernel of G, we need to solve the homogeneous system of linear equations whose matrix is the matrix of G in the standard basis. So we take the matrix of G in the standard basis and we reduce it to a row echelon form using Gauss elimination. So we use 1 here in position 1, 1 to kill this one. So we subtract row 1 from row 3. Rows 1 and 2 remain the same, and row 3 becomes 1 minus 1 is 0, 0 minus 0 is 0, 2 minus 0 is 2, 0 minus 0 is 0. Now we can divide row 3 by 2 to make this into 1, and we have the following row echelon form. So the first row is 1, 0, 0, 0, the second row is 0, 1, 0, 0, and the third row is 0, 0, 1, 0. So this is a row echelon form, and we can now write down the solution to our system of linear equations. So our leading elements are in columns 1, 2, and 3, so we use x4 as a free variable, and using our row echelon form we can express all other unknowns via x4. So the first equation says that x1 is equal to 0, the second equation says that x2 is equal to 0, and the third equation says that x3 is equal to 0. And for the free variable x4, we add the trivial equation that x4 is equal to x4. So if you rewrite this in the vector form, we get that the vector x1, x2, x3, x4 is equal to x4 times the vector 0, 0, 0, 1. So this vector 0, 0, 0, 1 forms a basis in the vector space of all solutions to our homogeneous system of linear equations. So this means that if we want to have a basis in the kernel of G, we should take polynomials whose coordinates is exactly the vector 0, 0, 0, 1. So this is a polynomial x to the power 3. The polynomial x to the power 3 has coordinates 0, 0, 0, 1 in the standard basis. And the above means that the polynomial x to the power 3 forms a basis in the kernel of G. Let us return back to our row echelon form and note that in our matrix the leading elements were in columns 1, 2, and 3. This means that if you look at the first 3 columns of the original matrix of G in the standard basis, these columns are linearly independent and span the column space. So this means that the image of G is spanned exactly by the 3 first columns in the matrix of G in the standard basis. So it is spanned by the vectors 1, 0, 1, 0, 1, 0, and 0, 0, 2. And this completes problem 1. Problem 2. Let A be the matrix 1, 1, minus 1, minus 1. It's a 2 times 2 matrix. Consider the linear operator F on the vector space of all 2 times 2 matrices, which sends a matrix X to the matrix AXA. Determine a basis in the kernel of F and a basis in the image of F. Solution. Similarly to the previous problem, if we want to determine a basis in the kernel and a basis in the image of a linear operator, we need to determine the matrix of this linear operator in some basis, and the usual choice is in the standard basis. The standard basis of the linear space of all 2 times 2 matrices consists of the following 4 matrices. The matrix E11, which is 1, 0, 0, 0. The matrix E12, which is 0, 1, 0, 0. The matrix E21, which is 0, 0, 1, 0. And the matrix E22, which is 0, 0, 0, 1. So let us compute what happens if we apply our linear operator F to all these 4 matrices. Applying F to E11, we get the matrix A times E11 times A. So let's compute what happens if we multiply A and E11. We will get the matrix 1, 0, minus 1, 0. And then, if we multiply this matrix again with A, we will get the matrix 1, 1, minus 1, minus 1. So F applied to E11 produces the matrix 1, 1, minus 1, minus 1. Let's go further. Let us apply F to E12. So this is a product of A times E12 times A. So if we multiply A and E12, we will get the matrix 0, 1, 0, minus 1. And now if we multiply this matrix with A, we will get minus 1, minus 1, 1, 1. So F applied to E12 gives the matrix minus 1, minus 1, 1, 1. Next, let us compute F applied to E21. So we have A times E21 times A. If we multiply A with E21, we will get the matrix 1, 0, minus 1, 0. If we multiply this matrix with A, we will get the matrix 1, 1, minus 1, minus 1. So F of E21 is equal to 1, 1, minus 1, minus 1. And finally, let us compute F applied to E22. This should be E22. So we have the product of A times E22 times A. And this is equal to the following matrix. So first we multiply A with E22. We will get 0, 1, 0, minus 1. And now we multiply this matrix with A again, and we get -1, -1, 1, 1. So let's look again at these matrices. So for the first basis vector, we have 1, 1, -1, -1. So the coordinates in the standard basis of this matrix are 1, 1, -1, -1. So for the second matrix, we have -1, -1, 1, 1. For the third, we have the same as the first. And for the fourth, we have the same as the second. So now we can write down the matrix of F in the standard basis. So the first column is 1, 1, -1, -1. So these are the coordinates of F of E11 in the standard basis. The second column is -1, -1, 1, 1. The third column is the same as the first one. And the fourth column is the same as the second one. To determine a basis in the kernel of F, we need to solve the homogeneous system of linear equation with this matrix, which is the matrix of F in standard basis. And if you look at this matrix, we see that all rows of this matrix are non-zero multiples of the first row. So the second row is just the first row, the third row is minus the first row, and the fourth row is minus the first row. So the rank of this matrix is 1, and so only the first row will survive in the row echelon form. So the row echelon form of this matrix just coincides with the first row of this matrix. And if we take the leading element in the first column, then we can choose x2, x3, and x4 as free variables. And from our one row, we can express that x1 is equal to x2 minus x3 plus x4. And for x2, we have the trivial equation x2 is equal to x2. For x3, we have the trivial equation x3 is equal to x3. And for x4, we have the trivial equation x4 is equal to x4. So in the vector form, the vector x1, x2, x3, x4 is equal to x2 times 1, 1, 0, 0, the coefficients 1, 1, 0, 0, plus x3 times the coefficients are -1, 0, 1, 0, this vector, plus x4, and then the coefficients are 1, 0, 0, 1. So this implies that these three vectors, which we see here, they form a basis in the space of all solutions to our homogeneous system of linear equations. So if we want to determine a basis in the kernel of F, we should take the three matrices whose coordinates in the standard basis are these vectors. So these are the matrices 1, 1, 0, 0, -1, 0, 1, 0, and 1, 0, 0, 1. So these three matrices form a basis in the kernel of F. Also, we fixed the leading element in the first column. So this means that the matrix whose coordinates are the first column of the matrix F in standard basis. So this matrix will form a basis in the image of F. And the first column of F is 1, 1, -1, -1. So this means that the matrix 1, 1, -1, -1 forms a basis in the image of F. And this completes problem 2. Problem 3. Construct, if possible, a linear map H from R3 to R3 such that the kernel of H is spanned by the vector 1, 1, 0, and part A, the image of H is spanned by 1, 2, 0, and part B, the image of H is spanned by the vectors 1, 2, 0, and 0, 0, 1. And when the problem says construct a linear map, it means give the matrix of this linear map in the standard basis. Solution. So this is the problem which relates the kernel and the image of some linear map. And in order to solve such problems, one often has to use the rank nullity theorem. Recall that the rank nullity theorem says the following. If F is a linear map from V to W, then the dimension of V is equal to the sum of the dimension of the kernel of F and the dimension of the image of F. For part A of our problem, we have that the original vector space from which H starts is R3. It has dimension 3. And part A asks us to construct an H for which the kernel is spanned by one non-zero vector 1, 1, 0. So the kernel will have dimension 1. And the image should be spanned by one non-zero vector 1, 2, 0. So the image will also have dimension 1. However, 3 is not equal to 1 plus 1. And this means that the rank nullity theorem says that such situation is not possible. So it is not possible to construct H as requested in part A of this problem, because the arithmetic invariants of such H contradict the rank nullity theorem. So let us now look at part B. So the difference in part B is that it requests that the image of H is spanned now by two vectors, and these two vectors are clearly not scalar multiples of each other, so they are linearly independent. So in part B, it is requested that the image of H should have dimension 2. So for part B, the dimension of the original space is 3. The dimension of the kernel of H, just like in part A, is 1. But now the dimension of the image of H is 2. And 3 is equal to 1 plus 2. So part B is consistent with the rank nullity theorem. So let's try now to construct such a map H explicitly. So let us denote by V1 the vector 1, 1, 0. So by our formulation, this is supposed to generate the kernel of H. In particular, H of V1 should be 0. In order to define a linear map, we should define it by its action on some basis. So now we know how H should act on V1. Let us extend V1 to a basis of R3. And the usual procedure of extension works as follows. So we write the coordinates of V1 as a column, and then the vertical line, and on the right of the vertical line, we simply write the identity matrix. In other words, the coordinates of the standard basis in our vector space. And we try to reduce this matrix to a row echelon form using Gauss elimination. So this is a short reduction. We have 1 in position 1, 1, and we kill 1 in the second row, first column. So we subtract row 1 from row 2. Rows 1 and 3 remain the same, and row 2 becomes 1 minus 1 is 0, 0 minus 1 is minus 1, 1 minus 0 is 1, 0 minus 0 is 0. So this is almost a row echelon form, with leading elements being this element in column 1, this element in column 2, and this element in column 4. So this means that the corresponding vectors, so the first column corresponds to V1, the second column corresponds to the first basis vector, and the last column corresponds to the third basis vector. So the vectors V1, E1, and E3 form a basis in R3. Let us denote this basis by bold V, and let us order it in the following order. So we start from E1, then E3, and then V1. So since we know that our H should be a linear map, it is uniquely determined by its values on E1, E3, and V1. And as we already mentioned, H of V1 should be 0 because it is requested that V1 should be in the kernel of H. Now it is also requested that the vectors 1, 2, 0 and 0, 0, 1 should generate the image. And one of the easiest ways to ensure this is just to say that let us assume that H sends the basis vector E1 to 1, to 0, and the basis vector E3 to 0, 0, 1. Then these two vectors will be automatically in the image. And so the image will be spanned by these two vectors, because the third basis vector is sent to 0. And for H, which we define in this way, if we consider the matrix of H, which starts from the basis V and ends up in the standard basis, we will get the matrix which we read column-wise 1, 2, 0, 0, 0, 1, 0, 0, 0. So because 1, 2, 0 is the image of E1 under H, 0, 0, 1 is the image of E3 under H, and 0, 0, 0 is the image of V1 under H. So this is a matrix of H in the basis E, V. So we start from the basis V and we end up in the basis E. So now it remains only to use the base change formula to get the matrix of H in the basis E. So the matrix of H for the standard basis EE should be equal to the matrix of H in our basis E and V times the transformation matrix from V to E. So this V as a lower index and this V as an upper index, they should cancel. So we need to find out what is the transformation matrix from V to E. What we do know, we know the transformation matrix from E to V. So we take elements in the basis V and write them in the standard basis as columns. So we have here the vector E1, this is a vector E3, and this is a vector V1, 1, 1, 0. But we need the matrix which is the inverse of this one. The transformation matrix from V to E is the inverse of the transformation matrix from E to V. So let's compute the inverse of this matrix. So we write this matrix, then the vertical line, and then the identity matrix, and we need to reduce it to a row echelon form such that we have the identity matrix to the left of our vertical line. So we start by swapping arrows 2 and 3 to get these ones on the diagonal. So now we have row 1 remains the same, row 2 is now row 3, and the original row 3 is now row 2. And we only need to kill this one, so we should simply subtract row 3 from row 1. Rows 2 and 3 remain the same, and row 1 becomes 1 minus 0 is 1, 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 0 minus 1 is minus 1, and 0 minus 0 is 0. So consequently, the transformation matrix from V to E is the matrix 1, minus 1, 0, 0, 0, 1, 0, 1, 0. This is the matrix which is on the right of this computation. Great, so now we can use the base change formula. The matrix of H in the standard basis is the product of the matrix of H between the bases V and E times the transformation matrix from V to E. The matrix of H between the bases V and E is the matrix 1, 0, 0, 2, 0, 0, 0, 1, 0, and the transformation matrix is 1 minus 1, 0, 0, 0, 1, 0, 1, 0. So if we multiply them, so the first row just gives the first row, 1 minus 1, 0. The second row here gives twice this first row, 2 minus 2, 0. And the third row here gives the second row here, 0, 0, 1. So we have the following answer. In part A, it is not possible to construct such H because we got a contradiction with the rank nullity theorem. And in part B, the following linear operator H, which has the following matrix in the standard basis, does the job. So the matrix is 1 minus 1, 0, 2 minus 2, 0, 0, 1, 1. Please note that the H constructed in this problem is not unique. There are many different linear operators which would satisfy the requirements of this problem. We just constructed one of them. So this finishes problem 3. Problem 4. Let F be a linear operator on R4 which has the following matrix in the standard basis. 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0. Find a basis in the kernel of F squared and find a basis in the intersection of the kernel of F and the image of F. Solution. Let us start by computing the matrix of F squared. So if you want to find a basis in the kernel of F squared, we need the matrix of F squared in the standard basis. The matrix of F squared in the standard basis is of course the product of the matrix of F in the standard basis with itself. So it's just the matrix 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, and the whole thing squared. So when we start from the first row, as an output we have the fourth row. So here we have as a first row the fourth row of the original matrix. As a second row we have the third row of the original matrix. and as rows 3 and 4, we will have the first row. So the matrix of f squared is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1. Great. So now we can find a basis in the kernel of f squared. For this, we need to solve the homogeneous system of linear equations with this matrix, which we just computed. So if we start with this matrix, we see that row 2 and row 1, they're the same, so we can just delete row 2. And row 3 and row 4 are the same. We delete row 4, and we immediately get a matrix which is in a row echelon form. And the leading elements here are the ones which are in column 1 and in column 4. So we can take x2 and x3 as the free variables, and then our system of linear equation reads, so the first row gives us x1 is equal to 0. Then we have the trivial equation for the free variable x2, x2 is equal to x2. Then we have the trivial equation for the free variable x3, x3 is equal to x3. And from the second row, we see that x4 is equal to 0. So in the vector form, the vector x1, x2, x3, x4, the left-hand side, is equal to x2 times the coefficient vector 0, 1, 0, 0, plus x3 times the coefficient vector 0, 0, 1, 0. This means that these two vectors, 0, 1, 0, 0 and 0, 0, 1, 0, that they form a basis in the kernel of f squared. So this finishes the first part of the problem. Let's go to the second part. We need to find a basis in the kernel of f intersection with the image of f. So let's start with the kernel of f. In order to find a basis in the kernel of f, we need to solve the homogeneous system of linear equations whose matrix is the matrix of f in the standard basis. So this is a matrix of f in the standard basis. We see that row 3 and row 4 coincide, so we can just delete row 4, and then we can swap row 1 and row 3. And here is the row echelon form for this matrix. The leading elements, they live in columns 1, 3, and 4. So we can take x2 as a free variable, and from the first row we have x1 is equal to 0. The trivial equation for x2, x2 is equal to x2. From the second row we have x3 is equal to 0, and from the last row we have x4 is equal to 0. In the vector form, x1, x2, x3, x4 is equal to x2 times 0, 1, 0, 0. So this means that the second basis vector e2, this is a vector 0, 1, 0, 0, forms a basis in the kernel of f. Great, but we need to find a basis in the intersection of the kernel of f with the image of f. So let's determine which elements in the kernel of f belong to the image of f. So since E2 forms a basis in the kernel of f, all elements in the kernel of f can be written as some scalar lambda times this E2. So let's determine for which lambda the vector lambda times E2 belongs to the image of f. In order to do this, we need to solve now the non-homogeneous system of linear equations, whose matrix is the matrix of f in the standard basis, and whose right-hand side is the vector of coordinates of lambda e2 in the standard basis. So here we have the vertical line. The left-hand side is the matrix of f in the standard basis, and the right-hand side is the vector of coordinates of lambda e2 in the standard basis. And we need to reduce it to a row echelon form using Gauss elimination. Again, we can delete the last row and swap row 1 and row 3, and we get this row echelon form. And we see that here we have 3 non-zero rows, both in the matrix to the left of the vertical line and in the whole matrix. So the rank of the matrix of the system is 3, and the rank of the extended matrix is also 3 for any lambda. So this means that the vector lambda e2 belongs to the image of f for any lambda. In other words, the kernel of f is actually a subset of the image of f. In particular, the intersection of the kernel of f with the image of f equals the kernel of f, and hence our basis vector e2, which formed a basis in the kernel of f, so the same vector forms a basis in the intersection of the kernel of f and the image of f. And finally, problem 5. Problem 5. Let A be a 4 times 3 matrix with real coefficients and of rank 3. Let G be a linear map from R3 to R4, which is given by left multiplication with this matrix. So starting from a vector v in R3, we can get a vector in R4 by multiplying v on the left with A. Determine the dimensions of both the kernel of G and the image of G. Solution. Let E1, E2, and E3 be the standard basis of R3. For any I between 1 and 3, if we multiply A with the basis vector EI, the outcome will be just the i's column of A. This means exactly that the matrix A coincides with the matrix of our linear operator G in the standard basis. So in order to determine which elements belong to the kernel of G, we need to solve the homogeneous system of linear equations with matrix A. We don't know A, so we cannot solve it explicitly, but we can theorize what happens. So let B be the row echelon form of A after we completed our Gauss elimination. So we know by assumptions that A has rank 3. This means that the row echelon form of A must have 3 non-zero rows. But we also know that it has 3 columns. So it is a 4 times 3 matrix with 3 non-zero rows, each having a leading element. And so the only possibility for this row echelon form is the following matrix: 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. So without knowing the matrix A, and only knowing that it has rank 3, we can explicitly determine the row echelon form. And now if you look at this row echelon form, we see that we have leading elements in each column. So there are no free variables at all, and this means that our homogeneous system of linear equations has only trivial solution. In other words, the kernel of our linear map G is 0. And so the dimension of the kernel is also 0. Using the rank nullity theorem, the dimension of the image of G is equal to the dimension of the original vector space. The original vector space is R3 minus the dimension of the kernel of G. The dimension of R3 is 3. We just computed that the dimension of the kernel of G is 0, and 3 minus 0 gives 3. So answer, the dimension of the kernel of G is 0, and the dimension of the image of G is 3. Here are some additional problems and questions. 1. Determine a basis in the kernel and a basis in the image of the linear map from Rx2 to Rx3, which maps f of x to x times f of x minus integral from 0 to x f of t dt. Question 2. Construct, by determining the matrix in the standard basis, a linear map from Rx2 to Rx3 whose kernel is spanned by the elements 1 minus x, x plus x squared, and 1 plus x squared. 3. Construct, again by determining the matrix in the standard basis, a linear map from Rx2 to Rx3 whose image is spanned by the elements 1 minus x, x plus x squared, and 1 plus x squared. Question 4. Construct, by determining the matrix in the standard basis, a linear map from Rx3 to Rx2 whose kernel is spanned by 1 minus x, and whose image is spanned by 1 plus x plus x squared, and 1 plus x squared. And finally, question 5. Let f from R5 to R2 be a linear map. prove that the dimension of the kernel of f is at least 3. Thank you very much and see you next time.